All right, let's get started. Welcome everyone to our second edition of Astronomy on Tap San Luis online. All right, let's get started. And welcome everyone to our... And well, sorry for the technical problem right there. Well, thank you so much again for tuning in for Astronomy on Tap San Luis online. We have Dr. Sophie Reed today and Ashley Walker for two talks on astronomy. But first of all, I would like to thank our sponsors, which would be Washington University in St. Louis, the Department of Physics, the Academy of Sciences in St. Louis, and we usually have our events at Urban Chestnut Brewing Company, but for the moment, that's not happening, of course. And also, we would like to thank the Solar System Ambassador Outreach Program of JPL. And we're going to get started right away with our first speaker, which is Dr. Sophie Reed. So I have the pleasure to introduce Sophie. We work together at Princeton University in the Vera Rubin Observatory project. And Dr. Reed got her undergrad degree in Cambridge University in the United Kingdom in natural sciences with a specialization in astrophysics. And she also got her PhD in astrophysics from Cambridge University as well. And she enjoys judo, rock climbing, ice hockey, and horse riding. So that's pretty cool. And she also enjoys giving outreach talks. So today she's going to talk about quasars. So please, Sophie, thank you so much for coming, and go ahead.
Sorry, I couldn't unmute myself from the shared screen button.
It's all right. We're bound to have technical problems as we already had, so we'll just own it. There you go. We can see it.
As Andres says, I'm Sophie. We work together at Princeton. And today I am going to talk about finding the earliest quasars. Now, in this sense of earliest, we mean those as close as possible to the beginning of the universe. So if you look out at the sun, don't look directly at the sun, but hypothetically look out at the sun. The light you see from the sun has taken 8 minutes to arrive to us. We are essentially seeing the sun 8 minutes back in time, approximately. You look out at stars at night and you're seeing those even further back. They're further away, so the light has taken longer to get to us. Eventually, if you want to look further back, the stars are too faint. They're too dim. You can't see them. It's like looking out at a candle. You can see it from a reasonable distance away. You look out at your house lights. You can see them from further away. But if you want to see a light source really far off in the distance, you need something really bright, like a big spotlight that you can see as far away as possible. Rings that we can see as far back in time as we possibly can, so that we can learn about the early universe. So the first thing to cover then is, what is a quasar? And bear with me, a quasar is a supermassive black hole, a really, really, really big black hole, like bigger than me post-quarantine baking. It is absolutely huge. And the bigger the black hole, the brighter it is, because we can see it, because the energy is conserved, and the gravitational potential energy of the matter that is falling into the black hole is heated up, and it is the S energy is emitted as heat and light. So the bigger the black hole, the brighter it is, or at least the brighter this infalling matter is, which is why we can see black holes at large distances. This only works for quasars, which are black holes that are eating their galaxy. If the black hole is starving, if it's hungry and it has got nothing nearby for it to eat, then it is completely black. You can't see it. Like the black hole at the center of the Milky Way, at the center of our galaxy, you can't see except for the dynamics of how nearby objects are moving around it. So we need these big, bright black holes, these big bright quasars. So if we want to find something, then we need to know sort of two things about it. We need to know how common it is, so how far we're going to look. Do we just need to check behind the back of the sofa? Or do we need to check behind a whole universe's worth of sofas before we're actually going to find one of these objects? And we need to know what it looks like. So first, let's think about how common they are. And to know about how common they are, we need to know a bit about how they're formed. So the formation process of these objects is debated amongst people. There's two main theories, that either they are formed when a star explodes, collapses, and dies. And this image on the right is of a supernova. It's there because it's very pretty. Or they're formed when a very dense area of gas directly collapses into a black hole. Now, in the early universe, the area we want to look at, it's much more, the matter is much more smeared out than it is now. So now, if you look up into the night sky, you see stars. You see these distinct clumps of matter. In the early universe, many stars hadn't formed. There hadn't been the time needed yet to form stars and a lot of galaxies. And the matter was much more evenly distributed into a kind of soup of hydrogen. So you had to find a dense patch of that, which then has to, as a denser patch, it has more gravity. So then more is dragged into it, and you can either form stars or dense areas for collapse. But this is rare. It's very rare for these patches of high density to form. And then once they have formed, they've got to grow to be these really, really big black holes, which are the only ones we can see. There are smaller ones, but they're not bright enough for us to be able to see them with our current telescopes. So it's incredibly rare. Like, you have to form it, and then it has to feed and eat so much stuff that it gets big enough that we can see it over these distances. So they're predicted to be really, really rare. And if you want to look for rare objects, you need to look over a large area, which is where the dark energy survey comes in. So the dark energy survey is the data that I worked with mostly for this project. It was a 6-year survey. It finished last year, and it took photographs of the night sky of most of the southern hemisphere. So it was very useful for this type of work. This is an image that is included just because it looks cool, which is when a meteor came past the telescope. So attached to this telescope is the dark energy camera called DCAM. It is 570 megapixels, which is a lot of megapixels and would be great for you to be able to have in your phone or to take normal photos with, but it has some downsides. High-def photos of people's faces don't always look great. And also it weighs, 4 tons, 4 tons, which is going to cause some serious jeans sagging unless you have a very good belt. But it is very useful for this type of work. It has got a really wide field of view, which means that you can take images of a larger area in less time. So we've got a good camera and we've got a good telescope to take photos of them. But as a rough estimate of how many there actually are. So this is just a brief skip ahead to how many we did, but with one stage in the project, we had data that covered 425,880,019 stars, galaxies, asteroids, all the other sorts of things you see in the sky. Based off previous attempts at these searches and theoretical models, we expected about 5 of these objects to be quasars, which is not that many. And it is equivalent, approximately, to looking for a needle in a haystack that is 5 meters by 5 meters by 100 meters high, which is about the height of the Statue of Liberty, including the base. This is an approximate size of a haystack. This does not take into account the fact that the way to the top of the haystack would be compressing the bottom of the haystack. And it had a very small sample size for the number of pieces of hay that I measured the size of, and subsequently piled up to find out how much they fluff in a pile, because at that point, the person who owned the hay and the yard, where I was supposed to be not making a mess, but in fact cleaning up, came out and asked me what on earth I was doing, and please could I stop. So now we know how rare they are. The other thing we need to know to find them is what they look like. At the beginning, I showed you a couple of pictures of them, absolutely stunning images. Those are nearby objects, and they're beautiful. Sadly, if you want to look at them at the beginning of the universe, you see these small red dots. Small red dots do not make as dramatic cover photos, so they get featured less often. Now, if you were on the ball when you looked at the images at the beginning, you might have noticed that they were bluer. They were not, in fact, small red dots. And that is because the universe is expanding. So these objects, and we know this from studies of quasars in the nearby universe, these objects emit a lot of ultraviolet and blue light. But the universe is expanding, and everything that is in the universe is expanding with it. So this stretches the light out. And what starts off as blue light, short wavelength light in the ultraviolet, gets stretched out to be this red light. It's red optical light and all the way into the infrared. So we know that they're going to look like red dots. This, combined with some features of the environment of the early universe, I said it's a kind of soup of neutral hydrogen, and that absorbs some of this short wavelength blue light, further increasing the amount of red light that there is. So we can split the light up. We take our telescope, and like if you used a prism to split light up and shine rainbows, or if you look through a candy wrapper, a translucent candy wrapper to see the different colors, we can do that with our telescopes. Essentially, you slot in what is a very expensive and probably slightly more sophisticated candy wrapper in front of the light, which allows you to split it up into sections. We name this a series of incomprehensible letters for historical reasons. But with the dark energy camera and with other complementary telescopes, we can look at the light all the way from the blue end of the visible light up into the infrared in sections. And this means that we can have a look for things that are red. So we can tell whether or not it's a quasar by looking at it in these different sections of light and seeing, is it not there in the blue? So the G on the left of this image, that is the shortest wavelength light, the bluest light. And it gets redder as it goes across through the optical and into the infrared light. And as you can see, in the first three of these images, there is nothing there in the middle. And then suddenly, as you move redder, it appears. So you can look for things that aren't there in a blue light and then are there in the red light. And this is the way we find them. So we do this, and we've been pretty successful at it. We've found the number that we expect to find, plus or minus a bit. Don't know whether we've found all of them, and we are still ongoing in our searches. But now we've found them, what do we do with them? Well, there's lots of things to be done with them. They're intrinsically very interesting objects. These are supermassive black holes right at the beginning of the universe. Theoreticians originally wondered whether theoreticians didn't think that it would be possible for them to have been formed in the time that we had. So just the sheer presence is very interesting. Knowing how many there are also helps to constrain models of how they form. They can be used to study the properties of the early universe. The environment that surrounds them is kind of imprinted into how they appear to us now. And as well as that, they're really bright. So you've got this beam of light shining from the beginnings of the universe all the way through to now. And in that beam of light is imprinted information about how the universe is evolving and changing. We know that it started from the Big Bang, and then it expanded rapidly, and then subsequent to that, it has been expanding ever since. We know when first galaxies were formed, but how the numbers of these objects that we can find, environment that surrounds the numbers of these objects that we can find and how they appear now allows us to put constraints on various theories about how the universe is evolving and developing. So that is all I have to say in this talk. I maybe gave it a little bit quick, for which I apologize. But are there any questions?
Okay, thanks, Sophie, for your great talk. So we have one question already in the chat. People, you can still ask questions. We have a 20-second delay, but I will still forward your questions. So Matthew wants to know, from the part about forming quasars, does the chance get affected by hydrogen versus deuterium or tritium?
I am having trouble hearing you.
Okay, so I'll ask again. So can you hear me now?
Yeah.
Does the chance get affected for forming quasars by hydrogen versus deuterium or tritium?
I don't really know. The chance for forming them is related to the density as opposed to like the makeup. And it'll also depend whether they are formed by the explosion of a star or by the direct collapse. Because if they're formed by the explosion of a star, then you're going to need the correct chemical makeup to trigger the formation of the star and then its subsequent explosion. I am not an expert in stellar astrophysics at all. So I don't know if deuterium, tritium affect how the star formation or supernova rates. You would need to ask somebody who knows things about stars rather than black holes. But I suspect that if it's direct collapse and it is formed just from an overdensity, then it probably doesn't matter too much because you just need it to be really dense.
We have a follow-up question. So how can you be sure you're looking at a black hole if the image is so small?
Well, so the first thing you do is you take these photos of it, which is what the images I showed. And then you take them to your friends who also know what quasars look like. And then you have a debate about whether or not this is what you think it is. And then maybe you ask another friend as well. And then you get excited or unexcited, depending on the results of these conversations. And then you apply to somebody who has a big telescope and say, I would like to use a spectrograph rather than a straight up camera. And a spectrograph gives you information about the light at every wavelength, rather than in these like coarse segments. So instead of dividing it up into 5 coarse blocks, you get information at every wavelength. And from this information, you can confirm that it is a quasar, because you have stumbled upon a problem that I didn't mention, which is there are other things that look like that. And there are other things that are much, much more common that look like that, notably brown dwarf stars, which are the bane of my research. And they look just like that, but I hate them. So the idea is not to observe those. And you can check that you're right using a spectrograph.
So Adam wants to know, what were the original causes of the uneven distribution of matter density?
What were the original causes of the uneven distribution of matter density?
Yes.
Well, I think that's just random fluctuations in the background matter field. Nothing is ever completely uniform. If you go back and you look at the cosmic microwave background data, which is from further back in time than we are looking, you can see that that is uneven and that propagates forwards. Just random chance, essentially.
Are there any more questions from the audience? I don't see any at the moment. So the follow-up from Adam is, so stochastic process leads to change in the interactions, etc.
Stochastic processes lead to change in... Yes, random chance causes density fluctuations.
So Juan wants to know, is it known for how long the activity bursts of these early quasars lasted?
That is a very interesting question and is a subject of much research, because if we knew that well, then we could do some really cool stuff with these objects. We have vague ideas based off like closer things and some maths, but it's not really known. There is discussion about this because we thought that there was a limit to how long they could be in this quasar phase, how much they could eat. We thought this was governed because as they get bright, essentially the force of the light can drive away stuff from it. Like, it's so bright, it's pushing matter back out. Radiation pressure pushes stuff back away from the object. Except that if this is true, it's barely possible to make these objects. So this is very debated at the moment. But you can look up the Eddington luminosity and the Eddington ratio if you want to learn more about it.
Okay, I don't see any further questions right now. So I guess thank you again for your great talk. That was really interesting.
There's actually one more question by Juan. It says, is it known for how long the activity bursts of those early quasars lasted?
I think we just answered that question.
Okay, sorry. but I had another question. You mentioned the dark energy camera that has 550 million pixels. Can you tell us a little bit more about the camera that is being built by the Rubin Observatory and how that's going to find quasars, or what are the expectations? And
I can tell you a bit more about it. So as Andres said, he introduced me. He and I work now for the Vera Rubin Observatory, which is going to have a better camera. I cannot remember the exact numbers. Please don't sack me, employers. I know somewhere out there is very interesting data about how many corgis you can fit in it. It's quite a lot. But it is going to be better in many ways. It is going to be more sensitive. So we're going to be able to see fainter objects. And it is going to be absolutely fantastic for this work. Like, really, really good. Because it's going to cover a wider area of sky. So we have chances of finding more of them, rarer ones. It's going to be more sensitive, particularly to the red light. So the dark energy camera is an optical camera. It's not super sensitive to the infrared because it's not an infrared camera. But we have made progress in making CCDs, which is the bit that goes in the back of the camera that detects the light, that are sensitive to both optical wavelengths and infrared wavelengths, so that you can use the same camera over a wider wavelength range. And that is going to be really, really good for this. So yeah, all in all, when Rubin comes along online, there is going to be a big scramble, and it's going to be really, really good for this science. The downside will be and it's a downside. There's going to be so much data. Like, it already takes quite a long time and quite a lot of effort to get through the like few 100 million objects that we had to study for this. When Rubin comes along line and this is multiplied by a lot, it's going to be a lot of sorting to find the 10 objects.
Oh, I have a follow-up question on that. So when you say all this data, how is it actually, how do you look at this data? Is this all done by hand by a million grad students, or what is the, I guess there's some neural network involved, or what do you use for technology here?
So this was done by a combination of grad student learning rather than machine learning and algorithm design. There is actually no neural net here. I know that there is upcoming work that I think has not been published yet to do something similar using machine learning. But this was done by comparing a variety of model data to real data and then finding what compared best, essentially. So we had some predictions made by other people in Cambridge of what we thought these quasars would look like. And we compared that with the model data. And actually it is fast. It takes about 2 days to do 5,000 square degrees of dark energy survey data.
So we have another question in the chat. Why do you look in the southern hemisphere?
Because they built the snazziest telescope in the southern hemisphere that I had access to during my PhD. This work has also been done from the north as well. So we put telescopes in high places with low natural light, no artificial light pollution. So the Atacama Desert in Chile is an excellent place for building telescopes. It's high, it's dry, and there is limited light pollution around it. So that is a good site for building telescopes. There are less places in the northern hemisphere that satisfy all these criteria that we have easy access to for building telescopes. There's Mauna Kea, but I didn't have access during the PhD to data from there. So these large-scale surveys have been based in Chile a lot, which gives you access to the southern sky.
Okay, great, thanks. So thanks again for your talk, and I hand over to Andres to introduce our second speaker.
Okay, thank you so much, Sophie. This was a very nice talk. And for our second speaker of the afternoon, in St. Louis, we have Ashley Walker. So Ashley Walker is an astrochemist and planetary scientist and science communicator. She received her Bachelor of Science in Chemistry from Chicago State University. And Ashley has interned at Harvard University and Johns Hopkins University, understanding the chemical evolution of the solar system. She's currently interning at NASA Goddard Space Flight Center in the SPICE Astrochemistry Lab. And SPICE stands for Spectroscopy for Planetary Ices Environments. In the SPICE lab, she specializes in the chemistry of planetary atmospheres and icy moons. She has been featured in an array of interviews, which includes Katie Couric's Thank You Notes and Adler Planetarium's My Adler Story. She advocates for students and highlights Black junior scientists during Black History Month. She is also the founder of #Black in AstroWeek. So we are very happy to have Ashley today with us, and welcome to Astronomy on Tap St. Louis. So Ashley, please go ahead and share your screen.
All right. And I believe we're good to go. So, hi everyone, my name is Ashley Walker, and I'm here with you all today to share about Black astronomers and everything that we go through as people of the African diaspora that face certain challenges. And if you all have been following in many hashtags, throughout these last few weeks. Last week was Black in Astro Weeks, which you can find a lot of the series, including my journey and my story, which I talked about on astrobytes.org. And so I was so happy to team up with them and talk about all of the events that were going on today. And don't worry, I got some science in here. So you all will be okay. I got some science in here. So let's get started, and I will go ahead and start talking about Black astronomers. Science is for everyone, no matter if you're young, old, doesn't matter your race, science is for everyone. And, you know, we have these, we think that science has limitations on folks, but in all actuality, it's for everyone. If you wanna, if you wanna do science and you're in preschool, you can do science, right? If you wanna be a stargazer later on in life, you can definitely do that. Science is for everyone. So no matter what people think or say, science is definitely for everyone. And so unfortunately, with the recent events of the Black Lives Matter movement, with the killing of Black people in America, these are things that are brought home to our own dear Black astronomers that have to deal with it every day. So my motivation, so I did a series of Black History Month highlights, which you can find on my Twitter, which at the end of this talk, I will give you my Twitter handle. You can find those Black History Month highlights, which I highlighted over 50 Black junior astronomers and talking about their work. And I talked about how amazing these students are. They're fabulous. And so in addition to that, again, me and AstroBytes collaborated with the Black in AstroWeek, which I am the founder. And so with this movement and seeing the impact all over the world, I really wanted to pay homage to my ancestors that could not or may not have been astronomers. And so some of them couldn't, right? Because of, if we think of, what has happened to Black folks, all with slavery and so on and so forth, and other horrific events, including the Civil War, including different types of civil rights movements, the Middle Passage, so on and so forth. These people could have been amazing astronomers, but this is something that we'll never know. And so currently, as it stands here in the US, it's 2% of Black people that are astronomers. So for the Black History Month, I had specific requirements because every year I'd be like, okay, cool, I want to see some new people. And, we'd see the same names. And I'm like, okay, I want to see new people. And this is where I came up with the idea, because I also want to showcase, there are a lot of us out here, right? There are a lot of historical moments that come from people of the African diaspora. And so with the requirements, you have to be, of course, from the African diaspora, a junior level student, undergrad, post-bac, or grad student, and has research in astronomy. So I have a bachelor's in chemistry, and that's all I did during undergrad. But I have research in astronomy, so that's all I did. And so I wanted to showcase that Black astronomers can come from all walks of life. You can be a geologist and be an astronomer. You can be a mathematician and be an astronomer. You can be an artist and be an astronomer. And I just wanted to show that we come from all walks of life. And so moving forward with my future Black history highlights, they will be surrounding all Black and STEM people. And that's an actual hashtag. So if you follow Dr. Stephanie Page, she is the founder of that which I need to really, really give her homage for that, pay homage to her, because she is amazing. And so she helped us find each other all on social media. Just a quick side note. Black in Astro Week, again, was started through all these murders of Black people throughout the years. Every time we turn around, we see the same old thing. The police or whoever gets away with killing an innocent Black person who did nothing. So I wanted to show like some of the barriers and obstacles that we face. Although, you know, a lot of folks see that we're like, oh man, that's so cool that you were the first and so on and so forth. Yeah, it is, but in the same sense, it's also very sad, because that means someone was before me and they left. And we will probably never know who this person is, right? So I wanted to show different obstacles that we go through, but I also wanted to uplift and bring them together. And this was something that was so beautiful to me that I just thought like, okay, I'm going to do this. And I had no expectations for it. I was just like, okay, I'm going to do it and it's going to go and we're going to be okay. And I didn't think that it will in this term, glow up. I didn't think that it would glow up the way it did. Right. And so I'm really, 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 really happy and really, really excited that, you know, this happened. And so I'm so grateful that everyone found each other. And I'm so grateful for my friends, Keyshawn, Iana, Cheyenne, and David, that all gave their experiences. So again, if you go to astrobites.org, you will see that. So Black undergrad students go through a lot. And so typically what we don't say and what we don't talk about is that there are some that are really the only ones in their department. And I've met quite a few. And it was very, 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 very sad to me. And I was like, oh my gosh, like what can I do to make you feel better? And so we want to give them a sense of community, right? Give them a sense of home, like you belong here, and just practice what we preach in terms of making departments better. There's quite a few RUs that are focused primarily on diversity and inclusion and specializes in Black and Brown students only. So I was a part of one, which I've met my amazing best friend and also Keyshawn, who I mentioned previously. And I also met my other best friend, Elizabeth Gutierrez, who was watching this. Hi, Elizabeth. So I'm just, really, really happy that there are some programs that can give us a sense of community within each other. And that once we go forward and go our separate ways, we'll still be in contact. We'll still be rooting each other on. We'll still have that community there. The Black graduate student experience can be, I'm not going to say can be, it is very tough from what I've seen and what I've heard. Now, I'm getting ready to transition into that experience. So I am speaking for my friends. I'm speaking for them, for the voiceless right now. And so the year between, basically to sum it up, by the time 2019 hit, there were at least 7 Black graduate students that had switched or were pushed out of PhD programs. And again, I should have changed that to 2, but there are at least, I believe it's at least 1% or 2% as a whole in astronomy. I'm not exactly clear on that, but it's a very small percentage of us, although historically our ancestors gave us the ability to understand astronomy. But there is some good news in Black astronomy. So as you can see, these students are amazing. And I just want to make sure that everyone knows some of their names. I couldn't get all of them on this talk, but there are quite a few. And so as you can see, Derek Carr, Sydney Duncan, who is a she's a real life ballerina. Like what? She's a ballerina and she studied physics, which is so amazing. John Lewis, who is at CFA. Miana Short, who graduated with a bachelor's in astrophysics from University of Wisconsin at Madison, and she was the first African-American woman. Jamila, who is my sister in astrochemistry, she will break barriers for all of us because currently there are no African-American women with PhDs in astrochemistry in the US. The first African-American man is believed to be Dr. William Jackson, who was at UC Davis. He graduated in 1961. So this is a huge gap from 1961, and she will be graduating in 2021. And so she will be the first African-American woman to receive a PhD in astronomy from Harvard, and the first African-American woman to receive a PhD in the concentration of astrochemistry in the US. And I am very much proud of her. Moya McTeer will also break barriers. She will, and these ladies, by the way, are graduating within the same year. They're all graduating next year, which I'm like, yes, I'm excited. So it's 7 African-American women graduating next year. And we are just like, okay. Moya McTeer will be the first African-American woman to receive a PhD in astronomy from Columbia. And she was the first person to receive a dual bachelor's in astronomy and folklore. So she's a folklorist and she does amazing work. And she's also an amazing psychomer. So you guys got to go check her out. She's in New York and she's doing a thing. Sinclair Manning will be the first African-American in general. Just they never graduated one. She will be the first African-American to receive a PhD in astronomy from UT Austin. So when we see these statistics, we hear these things, we do have to internalize how can we help these Black students and also our colleagues, also the professors, also the staff, how can we help them better? So right now I'm gonna move on into my science talk. So this is something, so I'm putting together 2 things that I did. One was at Harvard and one was at Johns Hopkins. So this is a protoplanetary disk, as I like to call it, a spinning pizza dish. And you can see like in certain spots where they have little like dots where it could be a planet forming. And so this is, to me, this is a beautiful schematic, by the way. I mean, I wish I could draw it. My drawing is pretty good, but it's not there. So what's a protoplanetary disk and how does it form? So if you look where it says molecular cloud, it has molecular hydrogen and molecular helium. And I like to say they come together as if they're in like a little argument and they're just like tussling. And they're like fighting and they're tussling. And it's like, you know, when you're watching them old cartoons and they're like getting ready to have a fight and they're just walking around each other in a circle. That's exactly how you want to think of what the molecular cloud is getting ready to turn into the protostar. And so they just keep spinning and spinning and spinning. And they keep spinning and spinning and spinning. And also, once they spin, as you can see, they have, you see like a little light coming. So that is the creation of the star. And so once you go down and you see like the chemical inheritance on the side that looks like little wings, and the little spinning pizza dish, as I referred to earlier, is what I studied. So I looked at hydrogen cyanide in protoplanetary disks, and we just wanted to see like somewhat what was going on with it, and it was really amazing, by the way. And the result is the solar system. Speaking of solar system, so we live on Earth, right? And a lot of people are like, oh, I want to go to Mars. I personally, I'm gonna be honest, I'm a little biased. Mars is great, but it's another place that I really like. It's, you know, it's another place that I really like, which is called Saturn's moon Titan. So if we think about Infinity War and Endgame, and that's exactly, yeah, I'm talking about Titan, but I don't think Thanos was gonna be there or it's that destructive. So I think it's safe. So Titan is beautiful to me. I believe Titan is just the best thing that ever happened to the icy worlds, right? And so it has its glow and it's very, very thick. The atmosphere is very, very thick and it's dense. And by the way, rumor has it that it's a real life shark though, because we can't like really see what's going on. So in the atmosphere. So yeah, that's what I kind of heard through the grapevine. But it actually is similarly to early Earth. And so we want to continue studying it to see what possible planetary habitability can be determined there and what chemicals are there. So again, Titan is beautiful. And it is the second largest moon in our known solar system. Our first largest moon is Ganymede. And back in October, we just found out that there were additional 20 moons. So that makes it, Saturn has 82 moons. And so it has a thick atmosphere. Again, it's compared to early Earth. So this is the upper atmosphere. And I don't know about y'all, but when you're in a plane and you know, you're going up on a plane and you know, you're looking at the altitude and you're going up high, don't that look similar to that? I mean, that's what I would think. So this is the upper atmosphere of Titan. And also you're looking at the haze, and that's what we want to know about. We want to know about the chemical evolution of its haze, the chemical composition of its haze. And so Titan has a couple haze layers. So this is when I was in Johns Hopkins, and that's the phaser chamber. I'm pretty sure. I mean, this was like the best thing ever, right? And this was the most, I'm telling y'all, this was the most beautiful chamber that I have ever seen. So if you look to your left, you have the Titan experiment. And if you look to your right, you have the exoplanet experiment. And so with Titan, we wanted to recreate the atmosphere in the lab. And while recreating the atmosphere in the lab, if you look at the glow in both the Titan and exoplanet experiment, you can see that, if you look at both, you can definitely see that it's doing dissociating and ionization. And so on my Titan one, I couldn't really get a really good pic of the particles, which is why I added the exoplanet one, which I took the picture of. And so you can see the particles forming, how light it's getting and it's forming. And once that's done, that's when we tested it to see what prebiotic molecules, what aerosol analogs could possibly form. And so I did this for my senior thesis defense, and I was very, very excited about it. And so as you can see, here's a comparison of Titan and early Earth, Titan and Earth. And as you can see, there are very, 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 very much similar things. And also I heard, and this is what my advice, again, I hear things through the grapevine. So I heard that, my former advisor said that you can fly on Titan, which I thought was cool. So you think of you being in like a Mortal Kombat movie or something, and you take two cardboard boxes and you fly them together. Well, what? That's something that I would want to do. I would want to fly on Titan. So So it's, this is just something that is so amazing. And as you can see, it has methane and ethane, water clouds. Titan also has rivers and lakes. It's just such a beautiful place that, no, it doesn't have oxygen, but it's beautiful. So we need to understand the solar system because we want to know the early events of life. And if we want to know everything that happened. And so this is something that is near and dear to my heart. I never thought that I'd actually be doing solar system astronomy, but this is something that I really, really, really enjoy doing. And we also want to make sure if we're trying to go into the future, we need to know what happened in the past. And that's the importance of the solar system. Thank you all so much. You can follow me on Twitter at that_Astro_chick. And follow AstroBytes on Twitter. And also I'm hosting Real Scientists. I'm curating Real Scientists for a week. So thank you all so much.
Thanks, Ashley, for your nice talk. I have to admit some of the hashtags, Black in Astro, Black in the Ivory, to read these stories was pretty eye-opening for me. So that was really interesting. So we already have a couple of questions. I tried to organize them to the parts of your talk. So the first question comes from Brian Kelly. So what specific advice do you have for high school astronomy teachers to encourage students of color to enter a STEM field?
So support them. So if you want to help them, like, for example, if you see, because there are like high school internships, NASA has high school internships, different places have high school internships. Make sure you say, hey, do you think this is I think this would be a good fit for you. Just hint it to them, because sometimes they may not see it as that. And so tell them, like, I think this would be a good fit for you. This is a once in a lifetime opportunity. Go ahead and take it. Also, like, do more activities, more STEM activities, STEM-based activities, astronomy-based activities. Also, you're more than welcome to share my Black History Month highlights or the Black in the Astro series with them to show them that it's people that look like you that are doing astronomy. And so typically when students don't see a reflection of themselves, they don't think that it exists. But we are here. And that was the point of Black in Astro.
Do you know a list of resources for high school teachers, or where you can find these internships and things like that?
Yes. So again, if you, I think it's NASA Education, if I'm not mistaken. I believe it's NASA Education, but there is a list of, if you, let me get her information. So, Michelle should have some. Her name is Michelle Aaron. She is a grad student at Johns Hopkins. Shout out to Michelle. She has a list of resources. And so also, if you try like if you're in the States, they have Upward Bound programs. They have RISE programs for students at colleges. You can also try like SACNAS, NSVP, Nobuche. They all have different, also the American Astronomical Society, they all have different things for high school students, different resources as well.
Great. Maybe we can collect them and we will Twitter them as well on our Twitter account for our followers as well. So there's also a science question. Does Titan show geological activity like volcanism? Does it have tectonic plates?
From what I know, I have no clue. Sorry about that, because I didn't do the geology part. I only did the chemistry part. So I only worked in like the air. So I'm so sorry, but I'm not sure.
Okay, then there is a question about the air. So how can we see what is beneath the thick atmosphere of Titan?
So right now, so Cassini actually went there. It kind of like, it flew by there. It was like, hey, it did like a little wave. It was like, hey, but they got Dragonfly coming, and Dragonfly is actually going to land there. So that's how we're going to find out. And it leaves in 2026, and it gets there in 2034. And I know that's a long time, but it's very exciting.
Are there any more questions from the audience? I don't see any at the moment. Maybe we wait another couple seconds due to the delay. Okay, if there are no more questions, or is there a question coming?
Yeah.
Oh, here's a question. So what do we know about ongoing construction efforts around the world for giant telescopes?
I'm sorry?
What do we know about ongoing construction efforts around the world for giant telescopes? Do you know any new planned giant telescopes or so?
No, I do not. Unfortunately, I don't.
Do you want me to also pipe in on this one?
Sure.
The general one. Some of them are ongoing. There's a bit of debate. Like, this is vaguely, roughly linked to some of what Ashley said earlier. There's been quite a lot of discussion about building new telescopes on Mauna Kea because it is a site of importance to the native population of Hawaii. And that is affecting building of some of the giant telescopes. It looks like Andres might know more about this than I do in that particular topic. So yes, there are some big ones coming in various places, but they are being delayed they're going ahead in the southern hemisphere, being delayed in the northern hemisphere. Of course, at the moment, everything is being delayed because of coronavirus. So who knows really how it'll all turn out.
Thanks. So we have one more question. What makes an atmosphere thick versus a thin atmosphere?
Well, we look at the chemical composition, and seeing like how much is there. And so with Titan, because it's like a foggy, like hazy place, that's how we determined it. And so it's mainly composed, the atmosphere, I think, is mainly composed of nitrogen, if I'm not mistaken. And but we're still trying to figure out what is the actual haze. So that makes it thick.
Thanks. There's also a question to all the telescope experts again. So do we know if the James Webb Space Telescope is affected as well, or are there any? Does anybody of us know more details about it?
Well, we know it got delayed again.
That's a kind of harsh question. Like, we'd all love James Webb to be launched. Will James Webb ever be launched? Will it explode? Who knows? Everything currently is delayed by coronavirus stuff. While those of us who work in the software side, like Andres and I, we can work from home fairly effectively within the bounds of working from home. The construction projects, the actual physical building of these things is being affected.
Great, thanks. So I think we're gonna end here. Thanks so much to both of our speakers. Thanks, Ashley.
Mm-hmm.
That was a great talk. I hand over to Andres for the last words and hope to see you all again soon at the next Astronomy on Tap.
Yeah, thank you. I just wanted to say thank you, everybody, for showing up on Astronomy on Tap online. And I would like to thank our speakers once again, Sophie and Ashley. And yes, I think I'll see you guys next time, hopefully in July. If not, we'll see. But thank you so much. Bye, everyone.